welcome to another module in this massive open online course. So, in this module let us start looking at digital communication systems. So, this will introduce you to the typical structure, alright, the typical working of a digital communication system. So, this module will focus on an introduction to digital communication systems. Okay. And if you look at a typical digital communication system, let us look at a schematic for a typical digital communication system. Okay. A schematic diagram of a digital communication system. A schematic diagram of a digital communication system will be as follows. I have a message signal that I want to communicate MT. Okay. In a typical analog signal, you simply modulate it and transmit this message signal MT. However, in a digital communication system, the process is very elaborate. First, it has to go, it is passed through an encoder. Okay. Now, what the encoder does is basically the encoder converts the message into a stream of bits. Okay. So, the encoder for instance, we have a stream of bits such as 0, 1, 1, 0, 0, 1. So, what the encoder is doing is taking your message and it is converting it into a stream of bits, and you might have seen in previous modules this is achieved through first sampling followed by quantization of the samples, alright, and representing the quantized samples, alright, using an appropriate, each sample can be represented using an appropriate number of bits. Alright. So, sampling followed by quantizer, that is quantizer, the sampling followed by quantizer converts this, and followed by this encoding operation converts the message signal, an analog message signal MT into a stream of digital information bits, that is a combination of binary information symbols, zeros and ones. Okay. Now, this stream of bits from the encoder is passed through a modulation, that is a digital modulation scheme. Okay. So, this is given as input to a digital modulation scheme, which is passed through a channel. Okay. So, this is then subsequently passes through a channel, okay, or let me write it this way, this passes through a channel. The channel can be of various types, it can be a wireline channel, it can be a twisted pair, or it can be a coaxial cable, it can also be a wireless channel, that is it can be a radio channel. Okay. We will look at some of these different channel types. Passes through a channel and the output is then passed through a demodulator. So, we have modulation operation and at the receiver we have a demodulator. Okay. So, we have a modulator, the received information bits are demodulated, followed by, of course, you have to pass it through a. So, at this point now you have the demodulated bits. Okay. So, basically you have 0, 1, 1, 0, 1, 1. Now, notice that purposefully I have written a different set of bits. For instance, if you look at here, alright, the fifth bit here, if you can closely observe, the fifth bit here is a 0. but the fifth bit here is a 1, and this is a very important point. The demodulated stream of bits need not be exactly equal to the transmitted stream of bits or the modulated stream of bits, alright. This arises from bit errors at the receiver. Okay. So, this is one of the important challenges in communication, correct. So, there are bit errors that arise during the demodulation process, alright, and naturally, alright, naturally it is desirable to have as few bit errors as possible, that is to lower or minimize the probability of bit error. In fact, this probability of bit error, that is the probability with which a received bit is in error, is a very important metric to characterize the performance of communication system, which we will look at in future modules, alright. So, this is something to keep in mind, right. The demodulated stream of bits is not exactly equal to the modulated stream of bits, and this arises due to various factors, for instance such as the noise at the receiver, the fading channel if the channel is a wireless channel, and so on, okay, and this is basically termed as a bit error, okay. This is followed by your decoder, okay. So, you have the stream of bits followed by a decoder, basically in which in the decoder you can basically convert the bits to your and followed by appropriate suitable. So, this is followed by a decoder, and this gives you your estimated signal m hat t, communication signal m hat t, okay. And if you notice, this chain corresponds to your transmitter, the top portion, that is all the operations before the channel, and the bottom portion, this corresponds to the operations at the receiver. That naturally goes without saying, because the operations at the transmitter performed at the transmitter modulated by a carrier frequency. So, the signal is encoded, converted to a stream of bits, digitally modulated, followed by multiplied by a carrier signal, then it is at the transmitter, then it is transmitted over the channel. At the receiver it is down converted, followed by demodulated, alright, and followed by decoding of the demodulated information bits. Okay. Roughly these are the operations that take place at the transmitter and receiver in a typical digital communication system. Okay. Now, the key parts of the theory of digital communication systems is basically how to design the various modules, how to design the various modules, namely how to transmit, what is the optimal transmit processing, how to receive, for instance, what is the optimal filtering operation that can be employed at the transmitter, what is the optimal modulation that can be employed at the transmitter, what are the modulation schemes. Okay. For instance, when you look at transmission, one thing you can look at is transmit filter. Okay. What is the energy or power of the transmit signal? What about the digital modulation schemes? Okay. And at the receiver also we can look at what are the receive filter, for instance, what is the optimal, if you are familiar with a communication system, how to design a filter such that the signal power is maximized, noise power is minimized, so that the signal to noise power ratio is maximized. Okay. What is the performance of different modulation schemes, for instance, what is the probability of error associated with the modulation schemes, which characterizes the ultimate performance. So, probability of error associated with the different. So, these are the various issues. So, there are several issues, right. So, which we are going to look at through the various modules, and some of these are basically how to design the different modules at the transmitter, how do you design the different modules at the receiver, and what is the overall performance, how do you characterize the overall performance of this communication system for the various purpose, for the various depending on the various modules that have been designed and incorporated for various purposes. Okay. And that is the main aim of this course, look at the overall working of a digital communication system and design these modules efficiently and also study their performance. Okay. Now, how to transmit the signal? So, in a digital communication signal, the transmitted signal corresponds to a series of symbols. So, naturally the transmitted signal corresponds to a series of symbols. Okay. For example, let us take a simple example. To start with, let us take a simple example. Let us say we take the information symbol 0, we map it. Okay. So, this is your these are your information. We have two information symbol 0, the binary information symbols, information symbol 0, information symbol 1. So, these are your information symbol 0, information symbol 1. Okay. This can be mapped. Now, we have to do transmission over the channel, we have to map it to physical signal. So, we have to map it to some voltage level. So, let us say this is mapped to the level minus A, this is mapped to the level. So, 0 is mapped to the level plus A and 1 is mapped to the level minus A. So, let us say these are two symbols belonging to the digital constellation. These are two voltage levels, or let us say these are two symbols belonging to the symbol belonging to the digital modulation, or this is also known as a constellations. So, naturally we have binary information symbols, these have to be mapped to a set of digital modulation, alright, symbols belonging to a digital modulation constellation. In this particular case, the mapping is very simple, 0 is mapped to minus A, 1 is mapped to the voltage level plus A, alright. So, there are two different voltage levels, minus A, plus A and minus A, and both of them are opposite in phase, alright. So, one has phase 0, the other has phase 180 degrees, alright, plus A and minus A, alright. So, therefore, this constellation which comprises of these two symbols plus A and minus A, which are different in the phases, right. One is the phase amplitude of both of them is same, that is A, the phase of one is 0, the phase of other is 180 degrees. So, we have two different phases, alright, it is a binary phase constellation. So, this is known as a binary phase shift keying constellation. It is one of the simplest constellations. We will look at several others as we proceed through the various modules. So, this constellation is termed as BPSK, that is your binary phase shift keying symbol constellation. Okay. And therefore, this is a mapping, alright. So, we are mapping it to a binary phase shift keying constellation, and this operation is termed as, basically this is nothing but a modulation. This operation is this mapping this operation is termed as operation, or rather digital modulation. Although conventionally we can simply call it as modulation, this is basically, more specifically, this is digital modulation, okay, where you are basically mapping the information bits, information symbols, binary information bits to symbols belonging to a digital constellation. Okay. So, now let us look at again our example below. Let we have this digital information bit stream. So, you can also call this series of digital information symbols as a bit stream. So, this is your bit stream, this is your bit stream, and for instance 0 we are mapping to, well, A, 1 we are mapping to minus A. So, we are mapping it to a digital modulation stream. Okay. So, this is a digitally modulated stream, minus A, minus 1 is mapped to minus A, 0 is mapped to A, 0 is mapped to A, 1 is mapped to minus A, and so on. So, this is the stream of digitally modulated symbols. This is the stream of digitally modulated symbols. Okay. Now, how do we transmit this? Obviously, we cannot just simply transmit the stream of digitally modulated symbols. So, I have to basically transmit some signal, correct. So, I cannot simply transmit a signal, I cannot simply transmit a voltage level. I have to take the aid of some signal, I have to transmit it over some signal, right, some physical signal that can be transmitted over the channel, alright. So, this is this signal, this particular template signal that you use to transmit these voltage levels of the digital modulation is termed as a pulse. So, this particular signal is termed as a pulse. How do we transmit the digital modulated symbols? So, we transmit transmit the digitally modulated symbols using a pulse. For instance, a typical pulse can be of the form. So, this is let us say a pulse PT. We have already seen an example of the pulse in one of the previous modules. Pulse can be of height 1 from minus t by 2 to t by 2. So, capital T is the width of the pulse. So, this is the width of the pulse or duration of pulse. This is the duration of the pulse. Pulse is from minus t by 2 to t by 2. This is denoted by P sub capital T of t, where P sub capital T of t equals, well, this is equal to 1 if mod t less than or equal to capital T over 2, 0, 0 otherwise. So, this is our pulse. Now, what we are going to do with this pulse, if I have to illustrate it in a very simple fashion, the first symbol, let us say this is my time axis. So, the first symbol is basically A naught into, so this is my first symbol of height A, because remember the first digital modulation symbol is A. So, this is A naught into Pt of t. So, take the symbol, multiply it by the pulse. Okay. Now, the second symbol is more interesting, you shift the pulse by t. Okay. So, you shift the pulse by, so this is from minus t by 2 to t by 2, you shift it by t. So, this is at 0. So, this shifted to t. So, minus t by 2 to t by 2 to 3 t by 2, that is, and multiplied by, so this level is minus a. So, shifted by t and multiplied by a1. So, this is a1 pt t minus t. So, shifted by t by t and multiplied by a1. Shifted by t and multiplied by a1. Second, you shift it, obviously the next one you shift it by 2t, that is therefore this will go from, well, t by 2, 3t by 2 to 5t by 2. So, shifted by t, okay. So, this will also be, since A2 is also, so shifted by 2t multiplied by A2. So, A2 pt minus 2t. Third symbol will naturally be shifted by 3t and multiplied by, well, A3. So, this will be 5t by 2 to 7t by 2. So, this will be multiplied by 7t by 2, and in fact, it will go on in this fashion, and this is A3 P3 Pt minus 3t. So, this is shifted by 3t, pulse shifted by 3t, multiplied by A3. So, what you are doing is corresponding to the kth pulse, you are shifting the pulse by kt, k times the symbol duration, and multiplying it by ak. That is the whole idea, and therefore, you are transmitting symbol, digital modulation symbol after symbol, right. Each symbol ak is transmitted in the kth duration, correct. So, it's you are transmitting, and the way you are doing it, the way it is done is by shifting the pulse by kt, multiplying it by the, or modulating it with the digital modulation symbol, that is ak pt minus kt. Okay. And now the net digital digitally modulated signal, alright, the digital communication signal that is transmitted corresponds to basically the sum of all these shifted and multiplied pulse, or shifted and modulated pulses. So, what we are observing is basically, it is very simple, it is therefore for kth symbol you have ak, the pulse p, I am just calling it pt minus kt, where p is any pulse, okay, not necessarily p subscript t, capital T. So, this is any pulse, okay, shifted by kt, where t is the symbol duration, and ak is a kth symbol. Therefore, the net signal, net transmitted digitally modulated signal or net transmitted digital comm signal is, you can call it xt, denoted by xt, xt is basically your summation k equal to minus infinity, because you can have an endless infinite stream of digital symbols p t minus kt, alright, and this is going to be your, this is your typically. So, you are transmitting symbol after symbol by shifting the pulse by k times t, where t is the symbol, capital T is the symbol duration, modulating it by the kth information symbol or kth digital modulation symbol, that is ak, alright, and the sum of all these shifted modulated pulses is what constitutes basically your digitally modulated the transmitted signal in this digital communication system. Okay. And therefore, this is your structure of a typical digital communication signal, which is very interesting. Okay. This is a structure of a typical transmitted signal in a digital communication system, structure of the of a typical transmitted signal in a digital communication signal. Alright. So, basically in this module we have seen a brief introduction to a digital communication system, a typical schematic diagram illustrating the various components or modules at the transmitter and receiver, and also incorporating the also showing the place of the relevance of the channel in this typical schematic of a digital communication system. And also we have seen an overview or a brief introduction to the process of mapping or modulation of the information bits to a digital modulation constellation, followed by the transmitted, the structure of a typical digital digitally modulated communication signal employing a pulse shaping filter. Alright. So, this PT, which is basically your pulse, is nothing but a filter, can be implemented as a filter. So, this is also known as a pulse shaping filter. Alright. So, we will stop here and look at other aspects in the subsequent modules. Thank you.